Global warming and climate change are terms for the observed century-scale rise in the average temperature of the Earth's climate system and its related effects. Multiple lines of scientific evidence show that the climate system is warming. Although the increase of near-surface atmospheric temperature is the measure of global warming often reported in the popular press, most of the additional energy stored in the climate system since 1970 has gone into ocean warming. The remainder has melted ice and warmed the continents and atmosphere. Many of the observed changes since the 1950s are unprecedented over decades to millennia. Scientific understanding of global warming is increasing. The Intergovernmental Panel on Climate Change reported in 2014 that scientists were more than 95% certain that global warming is being caused mostly by increasing concentrations of greenhouse gases and other human activities. Climate model projections summarized in the report indicated that during the 21st century the global surface temperature is likely to rise a further 0.3 to 1.7 degrees Celsius for their lowest emissions scenario using stringent mitigation and 2.6 to 4.8 degrees Celsius for their highest. These findings have been recognized by the national science academies of the major industrialized nations and are not disputed by any scientific body of national or international standing. Future climate change and associated impacts will differ from region to region around the globe. Anticipated effects include warming global temperature, rising sea levels, changing precipitation, and expansion of deserts in the subtropics. Warming is expected to be greater over land than over the oceans and greatest in the Arctic, with the continuing retreat of glaciers, permafrost and sea ice. Other likely changes include more frequent extreme weather events including heat waves, droughts, heavy rainfall with floods and heavy snowfall, ocean acidification, and species extinctions due to shifting temperature regimes. Effects significant to humans include the threat to food security from decreasing crop yields and the abandonment of populated areas due to rising sea levels. Possible societal responses to global warming include mitigation by emissions reduction, adaptation to its effects, building systems resilient to its effects, and possible future climate engineering. Most countries are parties to the United Nations Framework Convention on Climate Change, whose ultimate objective is to prevent dangerous anthropogenic climate change. The UNFCCC have adopted a range of policies designed to reduce greenhouse gas emissions and to assist in adaptation to global warming. Parties to the UNFCCC have agreed that deep cuts in emissions are required, and that future global warming should be limited to below 2.0 degrees Celsius relative to the pre-industrial level. On the 12th of November 2015, NASA scientists reported that human-made carbon dioxide continues to increase above levels not seen in hundreds of thousands of years. Currently, about half of the carbon dioxide released from the burning of fossil fuels remains in the atmosphere and is not absorbed by vegetation and the oceans. Observed temperature changes. The global average surface temperature shows a warming of 0.85, 0.65 to 1.06 degrees C in the period 1880 to 2012, based on multiple independently produced datasets. Earth's average surface temperature rose by 0.74 plus or minus 0.18 degrees Celsius over the period 1906 to 2005. The rate of warming almost doubled for the last half of that period. The average temperature of the lower troposphere has increased between 0.13 and 0.22 degrees Celsius per decade since 1979, according to satellite temperature measurements. Climate proxies show the temperature to have been relatively stable over the 1 or 2,000 years before 1850, with regionally varying fluctuations such as the medieval warm period and the Little Ice Age. The warming that is evident in the instrumental temperature record is consistent with a wide range of observations, as documented by many independent scientific groups. Examples include sea level rise, widespread melting of snow and land ice, increased heat content of the oceans, increased humidity, and the earlier timing of spring events, e.g., the flowering of plants. The probability that these changes could have occurred by chance is virtually zero. Temperature changes vary over the globe. Since 1979, land temperatures have increased about twice as fast as ocean temperatures. Ocean temperatures increase more slowly than land temperatures because of the larger effective heat capacity of the oceans and because the ocean loses more heat by evaporation. Since the beginning of industrialization, the temperature difference between the hemispheres has increased due to melting of sea ice and snow in the north. Average Arctic temperatures have been increasing at almost twice the rate of the rest of the world in the past 100 years. However, Arctic temperatures are also highly variable. Although more greenhouse gases are emitted in the northern than southern hemisphere, this does not contribute to the difference in warming because the major greenhouse gases persist long enough to mix between hemispheres. The thermal inertia of the oceans and slow responses of other indirect effects mean that climate can take centuries or longer to adjust to changes in forcing. Climate commitment studies indicate that even if greenhouse gases were stabilized at year 2000 levels, a further warming of about 0.5 degrees Celsius would still occur. Global temperature is subject to short-term fluctuations that overlay long-term trends and can temporarily mask them. The relative stability in surface temperature from 2002 to 2009, which has been dubbed the global warming hiatus by the media and some scientists, is consistent with such an episode. Recent updates to account for differing methods of measuring ocean surface temperature measurements show a significant positive trend over the recent decade. Warmest years: 14 of the 15 hottest years have been in the 21st century. While record-breaking years can attract considerable public interest, individual years are less significant than the overall trend. So some climatologists have criticized the attention that the popular press gives to warmest year statistics. For example, Gavin Schmidt stated, "The long-term trends or the expected sequence of records are far more important than whether any single year is a record or not." Statistical uncertainty means that it is hard to separate years where the temperatures are close. So while 2014 had a greater chance than any other single year, it only has a 38% to 48% likelihood of being the warmest year on record since 1880. 2014 was the 38th consecutive year with above-average temperatures. Ocean oscillations like El Niño Southern Oscillation can affect global average temperatures. For example, 1998 temperatures were significantly enhanced by strong El Niño conditions. 1998 remained the warmest year until 2005 and 2010, and the temperature of both of these years was enhanced by El Niño periods. However, 2014 was ENSO neutral. Initial causes of temperature changes. The climate system can warm or cool in response to changes in external forcings. These are external to the climate system but not necessarily external to Earth. Examples of external forcings include changes in atmospheric composition, solar luminosity, volcanic eruptions, and variations in Earth's orbit around the Sun. Greenhouse gases. The greenhouse effect is the process by which absorption and emission of infrared radiation by gases in a planet's atmosphere warm its lower atmosphere and surface. It was proposed by Joseph Fourier in 1824, discovered in 1860 by John Tyndall, was first investigated quantitatively by Svante Arrhenius in 1896. And was developed in the 1930s through 1960s by Guy Stewart Callender. On Earth, naturally occurring amounts of greenhouse gases have a mean warming effect of about 33 degrees Celsius. Without the Earth's atmosphere, the Earth's average temperature would be well below the freezing temperature of water. The major greenhouse gases are water vapor, which causes about 36 to 70% of the greenhouse effect, carbon dioxide, which causes 9 to 26%, methane, which causes 4 to 9%, and ozone, which causes 3 to 7%. Clouds also affect the radiation balance through cloud forcings similar to greenhouse gases. Human activity since the Industrial Revolution has increased the amount of greenhouse gases in the atmosphere, leading to increased radiative forcing from CO2, methane, tropospheric ozone, CFCs and nitrous oxide. According to work published in 2007, the concentrations of CO2 and methane have increased by 36% and 148% respectively since 1750. These levels are much higher than at any time during the last 800,000 years, the period for which reliable data has been extracted from ice cores. Less direct geological evidence indicates that CO2 values higher than this were last seen about 20 million years ago. Fossil fuel burning has produced about 3/4 of the increase in CO2 from human activity over the past 20 years. The rest of this increase is caused mostly by changes in land use, particularly deforestation. Estimates of global CO2 emissions in 2011 from fossil fuel combustion, including cement production and gas flaring, was 34.8 billion tons, an increase of 54% above emissions in 1990. Coal burning was responsible for 43% of the total emissions, oil 34%, gas 18%, cement 4.9% and gas flaring 0.7% in May 2013. It was reported that readings for CO2 taken at the world's primary benchmark site in Mauna Loa surpassed 400 ppm. According to Professor Brian Hoskins, this is likely the first time CO2 levels have been this high for about 4.5 million years. Monthly global CO2 concentrations exceeded 40 ppm in March 2015, probably for the first time in several million years. On the 12th of November 2015, NASA scientists reported that human-made carbon dioxide continues to increase above levels not seen in hundreds of thousands of years. Currently, about half of the carbon dioxide released from the burning of fossil fuels remains in the atmosphere and is not absorbed by vegetation and the oceans. Over the last 3 decades of the 20th century, gross domestic product per capita and population growth were the main drivers of increases in greenhouse gas emissions. CO2 emissions are continuing to rise due to the burning of fossil fuels and land use change. Emissions can be attributed to different regions. Attribution of emissions due to land use change is a controversial issue. Emissions scenarios, estimates of changes in future emission levels of greenhouse gases, have been projected that depend upon uncertain economic, sociological, technological, and natural developments. In most scenarios, emissions continue to rise over the century, while in a few, emissions are reduced. Fossil fuel reserves are abundant, and will not limit carbon emissions in the 21st century. Emission scenarios, combined with modeling of the carbon cycle, have been used to produce estimates of how atmospheric concentrations of greenhouse gases might change in the future. Using the 6 IPCC marker scenarios, models suggest that by the year 2100, the atmospheric concentration of CO2 could range between 541 and 970 ppm. This is 90 to 250% above the concentration in the year 1750. The popular media and the public often confuse global warming with ozone depletion, i.e., the destruction of stratospheric ozone by chlorofluorocarbons. Although there are a few areas of linkage, the relationship between the two is not strong. Reduced stratospheric ozone has had a slight cooling influence on surface temperatures. while increased tropospheric ozone has had a somewhat larger warming effect. Aerosols and soot global dimming. A gradual reduction in the amount of global direct irradiance at the Earth's surface was observed from 1961 until at least 1990. Solid and liquid particles known as aerosols, produced by volcanoes and human-made pollutants, are thought to be the main cause of this dimming. They exert a cooling effect by increasing the reflection of incoming sunlight. The effects of the products of fossil fuel combustion, CO2 and aerosols, have partially offset one another in recent decades, so that net warming has been due to the increase in non-CO2 greenhouse gases such as methane. Radiative forcing due to aerosols is temporarily limited due to the processes that remove aerosols from the atmosphere. Removal by clouds and precipitation gives tropospheric aerosols an atmospheric lifetime of only about a week, while stratospheric aerosols can remain for a few years. Carbon dioxide has a lifetime of a century or more, and as such, changes in aerosols will only delay climate changes due to carbon dioxide. Black carbon is second only to carbon dioxide for its contribution to global warming. In addition to their direct effect by scattering and absorbing solar radiation, aerosols have indirect effects on the Earth's radiation budget. Sulfate aerosols act as cloud condensation nuclei and thus lead to clouds that have more and smaller cloud droplets. These clouds reflect solar radiation more efficiently than clouds with fewer and larger droplets, a phenomenon known as the Dcoetzee effect. This effect also causes droplets to be of more uniform size, which reduces growth of raindrops and makes the cloud more reflective to incoming sunlight, known as the Albrecht effect. Indirect effects are most noticeable in marine stratiform clouds, and have very little radiative effect on convective clouds. Indirect effects of aerosols represent the largest uncertainty in radiative forcing. Soot may either cool or warm Earth's climate system, depending on whether it is airborne or deposited. Atmospheric soot directly absorbs solar radiation, which heats the atmosphere and cools the surface. In isolated areas with high soot production, such as rural India, as much as 50% of surface warming due to greenhouse gases may be masked by atmospheric brown clouds. When deposited, especially on glaciers or on ice in Arctic regions, the lower surface albedo can also directly heat the surface. The influences of atmospheric particles, including black carbon, are most pronounced in the tropics and subtropics, particularly in Asia, while the effects of greenhouse gases are dominant in the extratropics and southern hemisphere. Solar activity. Since 1978, solar irradiance has been measured by satellites. These measurements indicate that the sun's radiative output has not increased since 1978. So the warming during the past 30 years cannot be attributed to an increase in solar energy reaching the Earth. Climate models have been used to examine the role of the sun in recent climate change. Models are unable to reproduce the rapid warming observed in recent decades when they only take into account variations in solar output and volcanic activity. Models are, however, able to simulate the observed 20th century changes in temperature when they include all of the most important external forcings, including human influences and natural forcings. Another line of evidence against the sun having caused recent climate change comes from looking at how temperatures at different levels in the Earth's atmosphere have changed. Models and observations show that greenhouse warming results in warming of the lower atmosphere but cooling of the upper atmosphere. Depletion of the ozone layer by chemical refrigerants has also resulted in a strong cooling effect in the stratosphere. If the sun were responsible for observed warming of both the troposphere and stratosphere would be expected. Variations in Earth's orbital cycles vary slowly over tens of thousands of years, and at present are in a very slow cooling trend. The variations in orbital cycles may produce a glacial period about 50,000 years from now. Feedback. The climate system includes a range of feedbacks, which alter the response of the system to changes in external forcings. Positive feedbacks increase the response of the climate system to an initial forcing, while negative feedbacks reduce the response of the climate system to an initial forcing. There are a range of feedbacks in the climate system, including water vapor, changes in ice albedo, clouds, and changes in the Earth's carbon cycle. The main negative feedback is the energy the Earth's surface radiates into space as infrared radiation. According to the Stefan-Boltzmann law, if the absolute temperature doubles, radiated energy increases by a factor of 16. Feedbacks are an important factor in determining the sensitivity of the climate system to increased atmospheric greenhouse gas concentrations. Other factors being equal, a higher climate sensitivity means that more warming will occur for a given increase in greenhouse gas forcing. Uncertainty over the effect of feedbacks is a major reason why different climate models project different magnitudes of warming for a given forcing scenario. More research is needed to understand the role of clouds and carbon cycle feedbacks in climate projections. The IPCC projections previously mentioned span the likely range for the selected emissions scenarios. However, the IPCC's projections do not reflect the full range of uncertainty. The lower end of the likely range appears to be better constrained than the upper end of the likely range.